All right, moving on, let's talk about measures of dispersion. So far with our work in statistics, we've talked about how to organize data and sort of come up with visual summaries of data. And then in the previous lecture, we talked about how to find measures of center, mean, median, and mode. In this lecture, we're going to talk about measures of dispersion, which are measurements of how spread out the data is. And to see why we're interested in measuring the spread of data, let's consider the graphs below. And these graphs represent the number of chocolate chips in Subway cookies versus the number of chocolate chips in Quiznos cookies. And by the way, the data is completely made up. I made up this data, but I made it up just to sort of show sort of the difference between these two things. Because something that's interesting is that if you were to add up the number of or if you were to calculate the mean number of chocolate chips for this data set and the mean number of chocolate chips for this data set, you would find that they have the same mean, right? But they're very obviously very different data sets, right? This one is much more spread out than this one. So the mean or the measure of center that you use doesn't tell the whole story, right? And so this is why we're interested in measuring dispersion. Okay. So in this section, we're going to talk about two measures of dispersion: the range and the standard deviation. We're going to spend most of our time talking about the standard deviation because the range, as it turns out, is not a very good measure of spread. Okay, it's not a very good measure of dispersion, but it's a good starting point if you want to figure out how spread out your data is. So let's talk about the range, right? So the range of a set of data values is the difference between the maximum data value and the minimum data value. So it's the difference between the largest value and the smallest value. So let's calculate the range of the Subway and Quiznos data above. Right, so for the Subway data, looks like the largest data value is 30, right? So the cookie with the most chocolate chips in it had 30 chocolate chips, and the one with the least number of chocolate chips had 19 chocolate chips. And actually there were two of those, right? But 30 minus 19 would be the range of the Quiznos data. Or, sorry, the range of the Subway data, I should say. Okay, range for Quiznos, on the other hand, range for Quiznos would be 25 minus 23. Okay, so the Subway data was much more spread out than the Quiznos data, and you can see that in the range, because the range for the Subway data is 11, and the range for the Quiznos data is 2. But now suppose that two more Quiznos cookies are sampled, and that one of the cookies just so happened to have 19 chocolate chips, and the other one just so happened to have 30 chocolate chips. Okay, so in other words, you'd get this situation. And then the question is, what is the range of the Quiznos data now? So the new range for Quiznos would be the largest data value, 30, minus the smallest data value, 19. Okay, so now the range for the Quiznos data matches the range for the Subway data when you add in these extra two cookies. But that doesn't seem quite right, because just because you have these two extra cookies, I mean, but this still seems quite a bit more spread out than this, right? So that's not good, right? So how good would you say the range is at describing the spread of a data set? Not very good. Not very good, because it's describing these two sets as being equally spread out, and they're not. This set is is much more bunched together. You just happen to have a couple of extreme values, right? This set is definitely more spread out. So we want a better way to measure the spread, measure the amount of dispersion in a data set. So let's talk about the standard deviation then, right? So the standard deviation of a sample of n data values is denoted by the letter S. And we define S as follows. So the standard deviation is the square root of the, remember that this symbol stands for sum, so it means add them all up, right? So S is the square root of the sum of all of the x minus x bars. Remember that x bar is your sample mean, okay? Squared, divided by n minus 1. This formula can be a little bit tricky for students to use, and so I'm going to show you a couple examples of how to use it. I'd also like to discuss where this formula comes from, okay? But I'm going to do that later. So I'll describe where the formula comes from later. For now, let's just suffice it to say that, loosely speaking, what the standard deviation measures is the average distance that each data value is from the mean of the data set. Okay, so that's essentially what's going on here, right? It's like you're looking at, when you look at x minus x bar, you're looking at the distance that that data value is from the mean. And you're adding up those distances, and then you're dividing by n-ish, right? And so that's basically what's going on, is that S is trying to measure the average distance from the mean of each data value. So that's sort of like the general concept of what the standard deviation measures. Now, the larger the standard deviation is, the more spread out the data is. So, for example, the Subway chocolate chip data from the previous page, the one that was more spread out, that has a standard deviation of 2.6 chocolate chips, while the Quiznos chocolate chip data had a standard deviation of 0.7 chocolate chips. It was much more bunched together. So as you can see, the standard deviation does a pretty good job of describing how spread out the data is. The bigger it is, the more spread out the data. Okay. So let's talk about how to use this formula, and then we'll talk a little bit about where the formula comes from. Okay. So to use the formula, to calculate the standard deviation, the first thing we need to do is calculate x bar. We need to calculate the sample mean first, right? Then once we've done that, we need to find x minus x bar for each data value x in the data set. And this thing, x minus x bar, is called x's deviation from the mean. So we need to calculate the deviation from the mean for each value in the data set. Then once we've done that, we can square those values. Okay, so square each of the deviations from the mean in step 2. So in other words, we're going to calculate x minus x bar squared for each data value x. And then finally, we're going to add them all up. So then add up the squares of the deviations from step 3. So we're going to calculate this, the sum of all of these guys. So we're going to add them all up. Once we've done that, then we can divide by n minus 1. And then finally, we can take the square root. It might be nice for you to know that the number that you get before you take the square root is called the variance. Okay? The standard deviation is just the square root of the variance then, right? As you're following these steps, one way that you might find it helpful to organize your work is to create a table that looks like this. So you list off, first of all, you find the sample mean, but then you list off all of the data values, you list off the deviations, you list off the squares of those deviations, and then you add them up. Okay? So I'm probably going to organize my work into this table. Let's take a look at a couple examples. It says, compute the standard deviation of the following sample data. Okay? So 6, 7, 8, 9, 10, 11, 12, 17. Okay? So the first thing we need to do is calculate the sample mean. That's going to be 6 plus 7 plus 8 and so forth, all the way up until we get to 17. Then we're going to divide by 1, 2, 3, 4, 5, 6, 7, 8. Let's see what we get. Whoa, hold on. Let me try again. 6 plus 7 plus 8 plus 9 plus 10 plus 11 plus 12 plus 17 is 80. 80 divided by 8 would be 10. Okay, so there's the sample mean. Now I'm going to arrange my work into a table, right? So I'm going to list off all of the data values x. Then once I've done that, I can list off x minus x bar, right? The deviations from the mean. And then I can list off x minus x bar squared, okay? So let's do that, all right? So x, we've got 6, 7, 8, 9, 10, 11, 12, and 17. So the deviations from the mean, x minus x bar, remember x bar is 10, right? So this is really x minus 10. Okay, so if x is 6, 6 minus 10 is negative 4. 7 minus 10 is negative 3. 8 minus 10, 9 minus 10, 10 minus 10, 11 minus 10, 12 minus 10, 17 minus 10. Okay, so these are the deviations from the mean. Now I'm going to square each of those values. And remember, when you square a negative number, you end up with a positive number, right? Negative 4 squared is negative 4 times negative 4, which is positive 16. Negative 3 squared is positive 9. Negative 2 squared, negative 1 squared, 0 squared, 1 squared, 2 squared, 7 squared. Okay? So then the last thing that you need to do, and I've kind of run out of space, but then you total up these ones, right? So you say the sum, the total of all of these squared deviations is going to be 16 plus 9 plus 4 plus 1 plus 1 plus 4 plus 49, which is 84. Okay, so it's 84. Now that's not the standard deviation, but you're most of the way there. You're almost there now, right? So now we're going to use our formula. We're going to say, all right, so the standard deviation is the square root of it's the square root of the sum of the deviations squared divided by n minus 1. Well, I know that this part is 84, right? So that's going to be the square root of 84 divided by n. N is the number of values in the sample data. So in this case, n is 1, 2, 3, 4, 5, 6, 7, 8. Okay? So in other words, that's the square root of 84 over 7. Or in other words, 84 over 7 is 12. So this is the square root of 12. So then if you plug that into your calculator, square root of 12 is about, so it's 3.464101, blah, blah, blah. So it's about, I would say, if we round to one decimal place, it's about 3.5. So we'd say S is about 3.5. Okay? So at this point, it's worth noting that depending on how you round and depending on like let's say that you got a sample mean that was not a whole number and that you had to round it, well then you're going to get rounding errors throughout your answers, throughout all the remaining work that you get. So when you're doing the homework, the answer that you come up with might not be exactly the same as the answer in the back of the book, but it should be in the ballpark. And the reason that you might be getting slightly different answers from what the book has is just because of the way that the book chooses to round versus the way that you're choosing to round. Okay, so don't worry about it too much. As long as you're close, right? And by close, I mean you should be within like 0.3, 0.4, something like that of what the answer in the back of the book says. As long as you're close, then chances are you did the work correctly. Okay. So let's do another example. Let's do this one. 82, 77, blah, blah, blah. Okay. So step 1, calculate the sample mean. It's going to be 82 plus 77 plus 90 and so forth until you get to the last value, which is 88. Then you're going to divide by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's see what we get. 71 plus 62 plus 68 plus 74 plus 84 plus 94 plus 88 is 790. Divide that by 10 and you should get 79. Okay. So now I'm going to make my table. And I think I'm going to have to work really hard to squeeze it all in here because I've got too many values. That's okay. Okay, so I'm going to write them small. 82, 77, 90, 71, 62, 68, 74, 84, 94, 88. And then that'll still leave me just enough room to write down the total. Okay. So x minus x bar. Again, x bar is 79, right? So this is x minus 79. Okay. So let's see. I'm going to do 82 minus 79. That's 3. 77 minus 79 is negative 2. 90 minus 79 is 11. 71 minus 79 is negative 8. And so forth. Okay. Then I have to square all of those things. 3 squared is 9. Negative 2 squared is 4. 11 squared is 121. 64. Oh, 17. I think it's 289. 17 squared. 289. Yep. 289. 121. 25. 25. 15 is 225. Is that right? 225. Yep. 9 squared is 81. Let me add these things up. And we have 9 plus 4 plus 121 plus 64 plus 289 plus 121 plus 25 plus 25 plus 225 plus 81 equals 964. Okay, so the standard deviation is the square root of the sum of the squares of the deviation divided by n minus 1. So in this case, I know that this whole chunk of the formula I've already done, that's 964. N was 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 10 minus 1. So in other words, this is the square root of 964 over 9. 964 over 9 is not a whole number, right? 964 over 9 is like that, 107.1. So rather than changing it into a decimal, I'm going to leave it as a fraction, and I'm just going to take the square root of it as is. I'm going to say square root of 964 over 9. Make sure to put that whole thing in parentheses so that you take the square root of the whole thing. Otherwise, it'll just take square root of 964. Right? Okay. So that comes out to about 10.3. Okay, so there's the standard deviation of that data set. Okay, so that's how you use the formula from the previous page. That's how you calculate the standard deviation. Okay, and again, the standard deviation is a measurement of how spread out the data is. The larger the standard deviation, the more spread out the data. Okay, so together the mean and the standard deviation tell us a lot about a data set, right? The mean tells you where the center of the data set is, and the standard deviation tells you how spread out the data set is. So together they give you a lot of good information. For example, one thing that we know is that under certain conditions, this isn't true for all data sets, but for certain data sets, which we'll talk about a little bit later, we know that about 95% of the data are going to fall within 2 standard deviations of the mean, which is a very confusing statement when you first read it. But we're going to try to unpack this by looking at a couple examples, right? The idea is that if a data value is more than 2 standard deviations from the mean, either 2 standard deviations above or 2 standard deviations below, then it's a pretty unusual thing. So let's unpack this a little bit by looking at some examples. Okay. So suppose that a certain species of corn has an average height of 90 inches with a standard deviation of 5 inches. Okay. So the average height is 90, the standard deviation is 5. How tall is a corn stalk that is 1 standard deviation above the mean? Well, so remember, the mean is x bar, which is 90, and the standard deviation is s, and that's 5 in this case. My s's and my 5's look very similar. But anyway, so how tall is a corn stalk that's 1 standard deviation above the mean? Well, if the mean is 90, and if you're 1 standard deviation above that, and if a standard deviation is 5, then 1 standard deviation above the mean would be 95. Right? So let me say that again. If the mean is 90, and 1 standard deviation is 5, then 1 standard deviation above the mean would be 90 plus 5, which is 95. Okay, so we can write that down symbolically as follows. We can say if you're 1 standard deviation above the mean, so 1 standard deviation above the mean, then that means you're at x bar plus 1 times s. Okay, so that would be 90 plus 1 times 5, which is 90 plus 5, which is 95. So how tall is a corn stalk that's 1 standard deviation above the mean? It would be 95 inches tall. Okay, so the average height is 90 inches. If you're 1 standard deviation above the mean, then you're 95 inches. Okay. Well, so how tall is a corn stalk that's 1.5 standard deviations below the mean? Right? 1.5 standard deviations below the mean. So 1.5 standard deviations below x bar, that would be x bar minus 1.5 times s. So that would be 90 minus 1.5 times 5. Or in other words, 90 minus 7.5. 82.5, I think. Yeah. Okay. All right. So if the mean is 90 inches and the standard deviation is 5 inches, then you're 1 standard deviation above the mean if you're at 95 inches, right? And you're 1.5 standard deviations below the mean if you're at 82.5 inches, right? And when I say you, I mean a corn stalk, right? Okay, well, next question. Would it be unusual to find a cornstalk that is 97 inches tall? Well, one standard deviation above puts you at x bar plus 1 times s. We've already calculated this, right? This is 90 plus 1 times 5, which is 90 plus 5, which is 95. Two standard deviations above would put you at x bar plus 2 times s. That would be 90 plus 2 times 5. That would be 90 plus 10, which is 100. Okay, so 97, if you're 97 inches tall, then you're somewhere between one standard deviation and two standard deviations above the mean. We don't really consider that to be too unusual, right? Because again, we know that about 95% of data are 95% of the data are within two standard deviations of the mean. So it's only if you're above two standard deviations or below two standard deviations that that you're considered to be an unusual thing, right? An unusual height. So this is somewhere between 1 and 2 standard deviations above the mean. So it's not unusual, right? So 97 is less than 100. So no, it's not unusual. What about 103 inches tall? That would be unusual, right? So same work as part C. So C, part C. And then you can say, 103 is greater than 100. So yes, 103 inches is an unusually tall cornstalk. Okay. So anyway, I don't know if you'll have any examples in the homework like this, but it's a useful thing. I just wanted to give you an example to show you why we're interested in knowing what the standard deviation is, right? Because it kind of lets you know when you have really strange examples or really strange specimens. Okay. Here's another example, and you will have an example, or you will have a homework assignment that asks you a similar question to this. It says the table below gives the annual incomes of 8 families in thousands of dollars. So family A made $49,000, family E made $51,000, and so forth. Find the number of standard deviations family A's income is from the mean. So we want to know how many standard deviations from the mean is family A's income. Well, in order to find that out, first we need to find the mean. First we need to find out what the mean is. Then we need to find out what the standard deviation is. So let's do it. It's going to be 49 plus 51 plus 52 and so forth, all the way until we get to 52. We're going to divide by 1, 2, 3, 4, 5, 6, 7, 8. That's 408 divided by 8, which comes out to 51. So the average salary looks like $51,000, right? $51,000. Now we've got to find the standard deviation, right? What's the standard deviation? Okay, so I'm going to arrange this into my little table. So 49, 51, 52, 51, 51, 50, 52, and 52. And x bar was 51, right? So this is going to be x minus 51. So 49 minus 51 is negative 2. 51 minus 51, 0. 52 minus 51 is 1. And so forth, right? 50 minus 51, 52. Okay. Now we square those. 4, 0, 1, 0, 0, 1, 1, 1. Then we add them up. We get 4, 5, 6, 7, 8. Not much variation. Not much variation in this data at all, right? So this is not surprising. Okay, so S is the square root of the sum of the squares of the deviations divided by n minus 1. Okay, so that's going to be the square root of, this whole chunk is 8. N was 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is going to be the square root of 8 divided by 7. Square root of 8 over 7 is about 1.1. Okay, so I know that the mean is 51. I know that the standard deviation is about 1.1. And the question that we're wanting to answer is, find the number of standard deviations family A's income is from the mean. Well, family A's income is 49,000. So if you take the mean, 51,000, and you subtract off one standard deviation, about 1,100, right? 1,100. Then you're going to get a little bit less than 50,000. If you subtract off 2 standard deviations, you're going to get a little less than 49,000. So this is somewhere between 1 and 2 standard deviations below the mean. To find out the exact number, here's what we could do. We could say, well, I'm going to take family A's income. So let me kind of start a new thing. So I'm going to take family A's income of $49,000, and I'm going to subtract the mean income level of 51. That'll tell me the distance. That'll tell me the deviation from the mean. And then if I want to know the number of standard deviations, then I need to say, well, compared to the standard deviation, well, I'm not explaining this very well. Basically, I need to take family A's income, subtract the mean from it, and then divide by the standard deviation. This will tell me how many standard deviations I am below the mean, right? So this would be negative 2 divided by 1.1. That comes out to negative 1.8, about negative 1.8. Okay, so family A's income is about 1.8 standard deviations below the mean. Okay, so it's about 1.8 standard deviations below the mean. Okay, so that's that. The last thing I want to do, like that does it for examples. Just the last thing that I want to point out is where does this formula come from, right? So as we've said, the standard deviation is an attempt to measure something like the average of each data value's distance from the mean. Okay. Well, in order to find the average distance from the mean, we first need to figure out how far each individual we first need to figure out each individual deviation from the mean. So we compute x minus x bar for each data value x. Once we have the individual deviations from the mean, we compute their mean. But there's a slight issue here, right? Because the sum of the deviations from the mean is always 0, right? So this part, if you don't square these values, if you just have x minus x bar and then you add them up, well, remember x bar itself is the sum of x divided by n. You can distribute the sum across that subtraction, in which case the second one is just this thing multiplied n times. Anyway, you get 0. You don't have to understand all the details here, right? But the moral of the story is that if you don't square the values, you're always going to get 0. And so we square the values so that we make them all positive, right? And that way, when we add them up, we're not always going to get 0. Then we calculate the mean of the squared deviations. And since we want the average distance, not the average squared distance, we finish by taking the square root. So that's basically what leads us to this formula. We're dividing by n minus 1 instead of just n, and so that might bother you a little bit, because if you're taking the average, why don't you just divide by the number of values instead of dividing by the number of values minus 1? The answer to that question is kind of complicated. Basically, it's because when we calculate a sample standard deviation, it's really just an estimate for the true population standard deviation. And it turns out that if we divide by n, we'll be underestimating the true population standard deviation by a factor of exactly n divided by n minus 1. The proof of that fact is way beyond the scope of this course, right? But I just wanted to point out that that's why we're dividing by n minus 1 instead of just n, because basically we would be underestimating the standard deviation otherwise. Okay, but your main takeaway should be this. Okay, the standard deviation is a measurement of how spread out the data is. It's sort of the average distance of the data values from their mean. And the larger the standard deviation, the more spread out the data. Okay, those are the main takeaways. So that'll do it for our discussion of measures of dispersion.